Dear students, welcome to fifth part of named reactions in organic chemistry. In this session, we are going to discuss about 8 reactions. One is Gattermaan Koch reaction, second one Kolbe's electrolysis, third Volhard Zelinsky reaction, fourth one Hoffmann Bromamide degradation, fifth one coupling reactions, sixth Gabriel Thalamide synthesis, 7 Cannizarro reaction and 8 one is Carbylamine reaction. So with this 28 name reactions, we are completing named reactions in organic chemistry. We can see each reactions in detail. Before going to the topic, please subscribe my channel. Press the bell icon for notifications. Like, share among your friends and comment. Here the reaction is Gattermaan-Koch reaction. In this reaction, benzene is treated with carbon monoxide in the acidic medium in presence of anhydrous aluminum chloride to give benzaldehyde. Here, the function of anhydrous aluminum chloride is to work as a catalyst. It is an electrophilic substitution reaction. There are 3 steps in Gattermaan-Koch reaction mechanism. In the first step is formation of formyl chloride. Second step, formation of electrophile. Third step, formation of benzaldehyde. See, all these equations are given. Next is Kolbe's electrolysis. In Kolbe's electrolytic method, electrolysis of an aqueous solution of potassium or sodium salt of a carboxylic acid produces alkane having even number of carbon atoms at the anode. So, it is an organic reaction that is named after the renowned scientist H. Kolbe. Kolbe reaction is formally a decarboxylative dimerization of 2 carboxylic acids or simply carboxylate ions. The term decarboxylative dimerization means there is a loss of molecules of carbon dioxide and the alkyl groups join together directly. The reaction takes place in the presence of an electric discharge where the electrons play a key role. See, the reaction is given as follows. When we examine the reaction mechanism of Kolbe's electrolysis, there are 2-step radical process. In the first step, electrochemical decarboxylation that gives a radical intermediate which is unstable and highly reactive in nature. In the second step, radical recombination. The radicals being chemically active recombine with each other with the help of a covalent bond to form RR bond. Kolbe's electrolysis is used in the mass production of symmetric alkanes in the chemical laboratories and industries. The electrochemical oxidative decarboxylation of carboxylic acid salt that lead to radical which dimerize. It is best applied to the synthesis of symmetrical dimers, which in some cases can be used with a mixture of 2 carboxylic acid to furnish unsymmetrical dimers. Next reaction is Volhard-Zelinsky reaction or HVZ reaction. This reaction is used for the halogenation of carboxylic acid at the alpha carbon. This reaction was named after Carl Magnus von Hell, Jacob Volhard and Nikolai Zelinsky. The reaction is initiated by the addition of phosphorus tribromide, that is catalytic amount, and the further addition of 1 molar equivalent of diatomic bromine. The equation is given. Carboxylic acid is converted into alpha bromocarboxylic acid in the presence of Br2, that is bromine, phosphorus and water. HVZ or Volhard-Zelinsky reaction mechanism. In the first step, when the oxygen attack the phosphorus, hydroxide become a good leaving group. The bromine ion now attack the carbonyl cation, breaking carbon-oxygen pi bond and forming a tetrahedral intermediate. Since the hydroxide ion is now a good leaving group, it is expelled from the tetrahedral intermediate. In the second step, the hydrogen bromide donate a proton to the carbonyl oxygen. The resulting bromide ion formed is a weak base and therefore captures the hydrogen which was in the alpha position. The extra electron is used to form a double bond with the adjacent carbon and push the pi electrons of the carbon-oxygen double bond towards the oxygen. The positive charge of the oxygen is removed. Since the bromide ion recaptures a hydrogen, the catalyst is regenerated. Thus, the keto-enol tautomerization of the carboxylic acid achieved. The conversion of keto form to enol form is given. In the third step, the oxygen in the enol form put forth an electron pair to form a double bond with the carbon. The existing carbon-carbon double bond then attack a bromine atom and thus the bromination of the enol at the alpha carbon occurs. The bromide ion also removes the hydrogen bonded to the oxygen atom and forms another hydrogen bromide molecule which evaporates from the system due to the absence of water. In the last and the fourth step, with the addition of water, the acyl bromide is hydrolyzed to the carboxylic acid. The oxygen from water attack the carbonyl group, forming an intermediate. When the reformation of carbonyl group occurs, the bromide ion is expelled. Due to high reactivity of acyl bromide, it is a good leaving group. The water removed hydrogen then moves back into the carboxylic acid. See, all these mechanisms are illustrated. Next reaction is Hoffmann-Bromamide degradation. It is used for the conversion of a primary amide to a primary amine with one less carbon atom. This is accomplished by heating the primary amide with a mixture of halogen, that is chlorine or bromine, a strong base and water. See, the equation is given. Conversion of primary amide RONH2 to RNH2. That is, primary amide is converted to primary amine. Here examples are given like acetamide to methanamine, propanamide to ethanamine. When we examine the reaction mechanism of Hoffmann-Bromamide degradation, 6 steps are involved. In the first step, hydroxide ion of the strong base attack the amide. This amide is now deprotonated, leading to the formation of water and the anion of the amide. In the second step, the anion now attack the diatomic bromine in an alpha substitution reaction. The bromine-bromine bond break and N-bromamide is formed along with bromide anion. The third step, the N-bromamide is now attacked again by the base, leading to its deprotonation and the formation of water along with the generation of bromamide anion. In fourth step, this bromamide anion goes through rearrangement in a way that the ethyl group or any alkyl group which is bonded with the carbonyl carbon now bond with the nitrogen instead. Simultaneously, the bromide anion form leaves the compound. This leads to the formation of an isocyanate. The addition of water to the isocyanate leads to the formation of carbamic acid in a nucleophilic addition reaction in fifth step. The carbamic acid now loses carbon dioxide, giving a negatively charged nitrogen bonded to one hydrogen and the ethyl group. When this is protonated by the water, the required primary amine is formed in the last or in the sixth step. The reaction mechanism is given. Next is the coupling reactions. We already studied about various types of coupling reactions. Coupling reaction involves joining of two chemical species, usually with the help of a metal catalyst. An important type of coupling reaction is the reaction of an organic halide with an organometallic compound having the general formula Rm, which facilitate the formation of a new carbon-carbon bond. If the organic halide in this reaction has the general formula R-X, the compound formed as a product will have the formula R. The illustration is given in presence of palladium and base. In this equation, R1 and R3 denote alkyl, alkene or alkyne group, and R2 denotes an H group or an alkyl group. Note that X denote a halide group. Mainly there are two types of coupling reactions. First one is homocoupling reaction. The second one is heterocoupling or cross-coupling reaction. In homocoupling reaction, two identical chemical species are combined to yield a single product. In cross or heterocoupling reaction, two dissimilar chemical species are joined together to afford a single product. Important of homocoupling reaction is the Ullmann reaction. And other example are Woods reaction, pinnacle coupling reaction and Glaser reaction or Glaser coupling. For a cross coupling reaction, the example is Heck reaction. That means an aryl halide and an alkene undergo reaction. Other examples for cross coupling reaction are Grignard reaction, Sonogashira cross coupling, Suzuki coupling and Buchwald-Hartwig reaction. Next is the application of coupling reactions are employed in the synthesis of several pharmaceutical products. Many conjugated polymers are prepared via coupling reaction that involve the use of a metal catalyst. The Suzuki coupling reaction is also used in the synthetic production of complex compound. For example, used in the production of caparatriene, which is highly effective in the treatment of leukemia. Many natural products can be obtained via certain coupling reactions. For example, benzyl isoquinoline alkaloid can be synthesized with the help of Sonogashira cross-coupling reaction. Next reaction is Gabriel Thalamide synthesis. The Gabriel synthesis is a chemical reaction that transforms primary alkyl halide into primary amines. Traditionally, the reaction uses potassium thalamide. Name of the reaction comes from German chemist Sigmund Gabriel. The biggest advantage of using the Gabriel synthesis is the avoidance of over-alkylation. A good nucleophile in the form of an imide ion is formed with the reaction of potassium hydroxide with the thalamide. The imide ion execute a nucleophilic substitution reaction on the alkyl halide and create an intermediate N-alkyl thalamide. Hydrolysis or hydrazinolysis of this thalamide yield a primary alkyl amine. However, aryl amines cannot be prepared via Gabriel synthesis. Aryl halides do not undergo simple nucleophilic substitution. See, the illustration is given. Here thalamide convert into N-alkyl thalamide and forms primary amine. In this reaction, in the first step potassium hydroxide is used. In the second step an alkyl halide is used to convert N-alkyl thalamide. Then sodium hydroxide is used conversion of N-alkyl thalamide into primary amine. There are three steps involved in Gabriel thalamide synthesis mechanism. In the first step, potassium hydroxide is introduced to the thalamide and an acid-base reaction ensues. The hydroxide ion deprotonate the imide. The resulting proton is more acidic than any simple amine. That is, the two adjacent carbonyl-like groups offer resonance stabilization, generating a strong nucleophile, that is the imide ion. See, that is shown here. In the second step, the nucleophilic imide ion attack the electrophilic carbon of the alkyl halide. The nitrogen atom subsequently replaces the halogen in the alkyl halide and bond with the carbon itself. This results in the formation of an N-alkyl thalamide. That is also given below. In the third and final step, the mechanism that takes place here is quite similar to the base catalyzed hydrolysis of esters, with nitrogen attached to the R group instead of oxygen. The hydroxide ion attacks the carbon atom bonded to the nitrogen atom, cleaving the N-alkyl thalamide. The cation in the base attaches itself to the oxygen atom as well. It is important to note that the nitrogen atom attached to the R group bond with the hydrogen ejected from the hydroxide ion when the oxygen atom replaces it in the thalamide. Here the conversion into primary amine is shown. Next reaction is Cannizarro's reaction. Cannizarro reaction involves the base-induced disproportionation of two molecules of a non-enolizable aldehyde to yield a carboxylic acid and a primary alcohol. The mechanism of Cannizarro reaction include a nucleophile such as hydroxide ion is used to attack the carbonyl group of the given aldehyde, causing a disproportionation reaction and giving rise to an anion carrying two negative charges. See here, disproportionation reaction take place and form a dianion. In the second step, the resulting intermediate can now function as a hydride reducing agent. Due to its unstable nature, the intermediate releases a hydride anion. This hydride anion proceeds to attack another aldehyde molecule. Now, the doubly charged anion is converted into a carboxylate anion and the aldehyde is converted into an alkoxide anion. That is given in this equation. Carboxylate anion and alkoxide anions are formed. In the third step or in the final step, water offers a proton to the alkoxide anion which give rise to the final alcohol product. The reaction can proceed since the alkoxide is more basic than water. Now, the carboxylate ion give rise to the final carboxylic acid product when acid workup is used. The acid workup is required since carboxylate is less basic than water and therefore cannot obtain a proton from water. See, here the conversion of carboxylate anion to carboxylic acid is given. Then alkoxide anion converted into alcohol. Both the steps are given here. The final reaction is carbylamine reaction. Carbylamine reaction is also called as Hoffmann isocyanide synthesis. It is also called isocyanide test. The reaction of a primary amine in presence of chloroform and a base to synthesize isocyanates. The dichlorocarbene intermediate is very important for this conversion. Carbylamine reaction cannot be used to synthesize isocyanate from secondary or tertiary amine. See here, it is given ethylamine undergo reaction in presence of chloroform and alcoholic potash give ethyl isocyanide. Aniline react with chloroform and alcoholic potash give phenyl isocyanide. Then potassium chloride and water are formed here. Here also there are 3 steps involved. In the first step is the dehydrohalogenation of chloroform to give dichlorocarbene intermediate. This dichlorocarbene intermediate is very reactive. The electrophilic dichlorocarbene attack the nucleophilic nitrogen of the primary amine. The elimination of the hydrochloric acid lead to the formation of isonitrile. The carbylamine reaction is used to synthesize isocyanate from primary amine with the help of chloroform and a base. Carbylamine reaction can also be employed to test the presence of a primary amine in a given substance. Dear friends, thank you for watching. Don't forget to leave a like and please subscribe my channel.